Any questions about anything? So the midterm will be happening 8th of April, what it means is that the exam will be released morning. 8th of April is a Thursday. So the exam will be released morning of Wednesday, and you will have till evening of Friday to submit it. The exam should not take more than 2 hours, but you can take as long as you wish. And you can use notes, book, anything on the internet. If you find that the solution is posted on some internet forum already, you can use it. However, you cannot go and ask on the internet someone to solve it for you. So the flow of information should be one way. You can take information if it's out there, but you cannot go and actively engage in a discussion with anyone on it. And trust me, the type of exam it will be, it's easy for me to pick if things like that happen. It happened 2 years ago, and it is a funny story. I will tell you maybe after the exam. So the exam will like a big homework, slightly more complicated, but not too bad. And you can all do well. I mean, go through the notes carefully, go through the homeworks carefully, and that period, Wednesday morning till Friday night, there won't be anything on Slack. But until then, few of you are already asking questions. Please keep doing that. And if any one of your classmate thinks that they have a better answer than me or they can answer before me, please go ahead and answer. It's really a discussion, because these days we no longer meet in lobbies or after the classroom or anything like that, so we have to use Slack for that. Okay, so what were we doing before this spring break? We were talking about quantum statistics of particles. So why were we talking about this? Because we had developed our canonical ensemble, grand canonical ensemble, all this methodology, and we were looking at applications. So we looked at phonons, we looked at photons. For phonons, we looked at the mystery of why heat capacity goes as proportional to T cube at low temperature. For photons, we looked at black body radiation, and we were to derive formulae like that. So it was all nice. And this was kind of like our third application. The only difference here was that these are not quasi particles. They actually do have a chemical potential. So they could be electrons, they could be neutrons, they could be protons, something like that. And they have their own act. You cannot just create an electron out of nothing. There is a chemical potential here. So with this, we used a similar formalism. We said that the energy of the system will be given by looking at different eigenstates or energy modes that the system can have, and looking at the number of particles in that energy level. This will be the energy. And the total number of particles themselves will be coming from looking at how many particles do you have in each energy level. And then we realized that if we set up a canonical partition function for this, which is, so the canonical way would have been to look at Q of NVT, and that would have been going over all N1, N2, N3. Any of these can be zero, and then maximum it can be N, because we have N number of particles. So in a given mode, you cannot exceed N. And then e to the power of minus beta times the energy. So minus beta summation J and J epsilon J. And we did not really talk about the value of epsilon j. That comes in from the harmonic oscillator or some other model, but the energy levels have a certain value. The problem, if it was just this expression, then life would be simple. But the problem is that n1 plus n2 plus n3 plus dot 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 must be equal to n. So it becomes a restricted summation, and this is very hard. I don't know how to do this. It's really difficult. So that's why we took the grand canonical way to solve this problem. And the grand canonical way, we did not have to worry about this constraint of n1 plus n2 equal to n1 plus n2 plus n3 plus dot 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 equal to n, because the number of particles can fluctuate, it can oscillate. So we don't have any issues there. So for grand canonical ensemble, we wrote down our z as mu vt as summation over all microstates e to the power minus beta e nu minus mu and nu. And then we used these two formula in here in the summation. We use both of these formulae, and then we wrote down through this the derivation that we came up with was that Z is equal to, let's write it down in a compact manner. We came with the final expression that we calculated was that Z mu Vt is equal to product over all states that you can have of 1 plus or minus e to the power minus beta epsilon j minus mu. And if you take a plus over here, this also has to be a plus 1. If you take a minus, it has to be a minus 1. And this way, we wrote down the formula for both Fermi-Dirac and Bose-Einstein. What is a quick way to remember which one is Fermi-Dirac and which one is Bose-Einstein? Is the plus, which one is Bose-Einstein? Is it the plus or the minus? And what's a quick way to remember? Any ideas? You can unmute and say.
The sum that doesn't diverge should be Fermi-Dirac. The one that diverges should be Bose-Einstein.
The one that diverges should be Bose-Einstein. Correct, Grishma. So which one do you think will diverge? One plus or one minus?
The one minus, because it goes
correct,
to the
exactly.
denominator.
So if I write this, it is correct, right? In the subscript, I write FD and Bose-Einstein, where the idea being that FD corresponds to plus and Bose-Einstein corresponds to minus. So this is a compact way of writing this. Great, thanks. And from this, we derived the average number of particles in a certain state in J. And that again came out to be Fermi-Dirac and Bose-Einstein. It was 1 over e to the power beta epsilon j minus mu plus minus 1. And you can see the divergence Grishma was talking about here. If you set epsilon j is equal to mu, then that particular energy, that particular state for Bose-Einstein, which is for this minus sign, will have a divergence because you will have 1 minus 1 and things will diverge in that state. So that was the phenomenon of Bose-Einstein condensation. So this was our summary. Now, what I would like to do next is to see, and you can call it application 4 if you wish, but it's really looking at this in a deeper way, is what happens to quantum statistics of particles as temperature is increased and density is decreased. Or in other words, as we approach the classical limit, what should happen to these bizarre looking distributions that we just wrote down over here? So actually, let's call it Z as equation 1 and this one as equation 2. So let's say you did not do any of this. All I am telling you, and let's go to next page for this, that you have capital N indistinguishable particles that exist independent of each other in a classical world. Okay, there is no quantum. Let's say this is, so this is what we would like to be able to recover from that. Can we write down the partition function for this one? So let's say, and then you have done something similar in your homeworks. Let's say the partition function for one such particle is Q1. Okay. So what will be the partition function for the full system in terms of Q1? Any idea? How should I proceed with this? What should I do? They are independent. So
is just Q1 to the power n.
okay, but that's the right step. But remember this one? The indistinguishability.
Oh, yeah.
So how should we deal with that, Nathan?
Hmm.
1 over n factorial.
Oh, okay.
That's my simple trick. Now, thanks. So this approximation that I wrote down, in your next homework or maybe your midterm, I will give you a problem where you will have to think about this. What would have happened if you did not put in n factorial? You would have led to some strange conclusions. In fact, this was called Gibbs paradox, where people did not really think of it, that classical particles are indistinguishable. So this is the partition function that we expect for the system. Let's go one step further. In terms of the model that we described earlier, for one particle, we can write, and this is canonical partition function that we are talking about, okay? For one particle, we can write down that the canonical partition function should be going over all states and simply doing e to the power minus beta epsilon j, right? This is Q1. We know the energy states, we just go and calculate whatever it is, that's it. So in other words, we expect that Q for the n particle system should be 1 over n factorial summation j e to the power minus beta epsilon j to the power n. This is what I would have written, assuming a classical picture and correcting for indistinguishability by dividing by n factorial. So, and I'm just going to omit this qn because we are talking about the full, it's let that be implicit. When there is no subscript, we are talking about the full partition function. So we have q is equal to this, which we expect from classical world. But at the same time, we wrote down a very funky looking grand canonical partition function, which doesn't quite look like this, right? It has some terms, but it doesn't quite look like this. So the puzzle that we have now, the question we have now is, does equation 1 imply equation 3 in high temperature, low density limit? If it does, then we know that life is consistent because quantum mechanics should reduce to classical mechanics in this limit. If not, then we have an issue. So that's what we are going to do now. So in order to do this, so this is really our puzzle that we are going to look at right now. It's not that hard. One, the thermo becomes a bit fun because you have, remember here we have the grand canonical partition function, and here we are talking about canonical partition function. So we'll have to do a bit of manipulations, but let's work it through systematically, and it's quite insightful. And then later we will also see, we will quantify this. What does it mean? What is the meaning of what exactly is this limit? So let's start this by talking about number of particles n is equal to summation j nj. Okay, so now we are starting from equation 1. So we are talking about the grand canonical setup, right? So n can fluctuate in the grand canonical ensemble. So therefore average number of particles is this thing, right? So now we can write down the value for this because we wrote average nj in equation 2. So this is going to be summation j e to the power beta epsilon j minus mu plus minus 1 to the power minus 1. And where again, if you forget, you should remember the minuses always show up for Bose-Einstein. So the plus is for Fermi-Dirac, minus is for Bose-Einstein, but I'm not going to always drag this FD and BE. And remember, I want to show this for both Bose-Einstein and Fermi-Dirac. It should happen, irrespective of whether you were considering only 2 particles in each state or any number of particles in each state. You should still recover this equation 3.
Quick correction. Can you go back to the last page? I think you got the sign wrong, right? Yeah, like the equation 1 should be like e to the minus beta or something plus or minus 1 or something.
I don't think so. It's correct.
Yeah, okay, never mind. Yeah, I think I got it.
No problem.
Yeah.
It's good to check. It's always good to check. So, okay, so we have this average number of particles. Now let's proceed from here. We haven't yet, this is exact, we haven't talked about low density or anything like that. So now let's talk about what do we mean by density. So density, rho, is average number of particles divided by volume, right? This is our thermodynamic density. So at high temperatures and low density, and this is where the physical picture comes in. If you imagine your states that look like Nj, and here, let's say you have state number 1, state number 2, state number 3, state number 4, state number 5, state number 6, dot, 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 so this has energy epsilon 1, this has energy epsilon 2, epsilon 3, epsilon 4. So if you go to a very high temperature and a low density, what will happen is that it will become extremely rare for you to find a state with more than one particle in it, right? First of all, it's high temperature, so it's easy to occupy higher energy states. States in this direction, you can easily occupy them because you're allowing for high temperatures. And secondly, the density is low. So why should you have two particles in the same box? So this will look something like 0, 1, 0, 0, 1, 1, 0, with a very, and dot, dot, dot. Each state will either have 0 or 1. And this has nothing to do with Fermi-Dirac or Bose-Einstein. So you can already see why the pictures might start to look similar, because already we are kind of seeing that at high enough temperature, there is no reason, and low density, there is no reason to pack two of them into the same state, because the thermal fluctuation will just be able to take it to the other side and keep bouncing around. So this means that at high temperatures, there are more single particle states than particles. Does that really help? Nah, let's ignore that one. Let's ignore this line. This doesn't help. I don't know why I wrote it. Forget about it. So what it really means is that lots of states are accessible because we are at high temperature. And if you look at any given state and calculate its Nj, it's going to be on an average much smaller than 1. This is the key thing that one should understand. Sometimes it can be confusing because we have so many states that are populated, and most of them are either 0 or 1, and we can keep populating higher energy states. Therefore, if you look at any given state on an average, its average occupation number will be much smaller than 1. And this is because lots of states are accessible. In fact, now I should write the statement I wrote earlier, number of states is much more than number of particles. And again, why? Because we are talking about low density limit, right? One way to approach low density limit is to reduce the average N or increase the average volume. So we are reducing the average N. So Nj for any state is much smaller than 1. Okay, so this is something that one of you might ask me 5 minutes later, I'm sorry, I didn't quite get that. And if you do that, it's totally okay because it's a subtle point. Let's call this equation number 5.
Yeah, Professor, when you say the average of Nj is lesser than 1, exactly what that means? Like Nj can be either 0 or 1, right?
Yeah, sure. So think of it this way. Let's say.
So I understand it's like it's more likely to be vacant than occupied.
That's all we are saying.
Okay.
So it's like I have what's a good example? It's like I have 50 different boxes to put my shoes in, right? And I have only 2 pairs of shoes. So on an average, any box, what is the number of shoes you will have in that box? 2 divided by 1 divided by 50, right? Do you see my point?
Yeah, yeah.
That's the idea here. So it's a subtle point, but it's important because why is this important? If you use this, equation 5, and so let's write down again in this page clearly, because these are all easy but subtle arguments. So we just said that average NJ is much less than 1 in low density high T limit. But we also said that equation number 4, that average NJ is equal to e to the power beta epsilon j minus mu plus minus 1 to the power minus 1, right? So if you combine these two, we lead to the conclusion that e to the power beta epsilon j minus mu, therefore, must be much more than 1, right? Because what is this? This is 1 over e to the power beta epsilon j minus mu plus minus 1, right? So, and if this whole thing is much smaller than 1, then the denominator must be much larger than 1. And in the denominator, the only thing that can be really much larger than 1 is this first part. Therefore, e to the power beta epsilon j minus mu is much, much more than 1 for both FD and Bose-Einstein. Okay? In other words, Nj is equal to, if you go to this equation and if this thing is much more than 1, then what is the point in dragging this one, right? It doesn't matter if it's much more than 1, whether you subtract 1 or add 1. It's like Jeff Bezos, I was reading somewhere, Jeff Bezos' net worth in a given day fluctuates by $20 billion, right? Because of Amazon stock. So if you take $100 from him, it's not going to make much of a difference. He doesn't seem to feel that way, but that's another story. So this is approximately e to the power beta epsilon j minus mu for both FD and Bose-Einstein, right? When is this true? At high temperature and low density, okay? Not otherwise. So now let's go back to our equation for N. N was summation J, average Nj, and we can write this as summation J e to the power beta epsilon j minus mu is equal to, oh wait, I missed something.
Shouldn't the average particle number be e to the power minus beta epsilon?
Yeah, exactly. This should be minus.
No, I think in the next page.
No, this is
should be-
plus.
yeah.
This is correct because I have a minus 1 over here. You're right. That is correct. I did not make a mistake there.
The approximate, the box equation, shouldn't that?
Yeah, because when I put this equal more than minus 1, this minus 1 has to be absorbed. Therefore, it's a minus 1, right? It is this minus 1 that is to be absorbed. Yeah, correct. Yeah, I was myself like, wait, what happened? So now this becomes e to the power plus beta mu, e to the power minus beta epsilon j. Suddenly you can see some glimmer of hope. Something like a canonical partition function is starting to show up, but we are not quite there yet. Or the chemical potential now, e to the power plus beta mu, is equal to average n divided by summation j e to the power minus beta epsilon j. Or I'm basically writing the same thing in a few different ways. Now, if you look at nj, that is this thing can replace this thing, right? Because e to the power plus beta mu is equal to this much. So average nj is given by n e to the power minus beta epsilon j divided by summation e to the power minus beta epsilon j j. In the classical limit, high T, low density for Fermi-Dirac or Bose-Einstein. Have we seen this relation before? Not maybe in StatMech, but maybe much earlier. Does this look like something we have seen? This is the classical Boltzmann factor, that the population of any state is proportional to e to the power minus beta epsilon j. This is a proportionality constant, right? This is total number of particles. This is summing energy exponentials over everything. So the only thing that is really varying for a state is e to the power minus beta epsilon g. So here you are saying that the population of any state is proportional to e to the power minus beta epsilon j. And this is something you all have used at some point or the other, intuitively or explicitly. Anytime you have a reaction, let's say you have some energy versus some coordinate, and you have a reaction in state 1 going into state 2, and you say, oh, this is the transition state, and the probability of being in the transition state is proportional to e to the power minus beta ETS, right? These type of approximations we always make, the Boltzmann approximation. But this is true only in the classical limit. So we can see something is good. We recover what we expect, the Boltzmann classical limit. We are not quite done with this partition function yet. So let's keep progressing from here. So how do we go from here? The problem is that we have z mu vt and we want to talk about q and vt. So we need to connect these two things. So this part of this class is even more general than what we have done for a bit, because we are going to connect two partition functions. How do we do that? So we know that minus beta a is equal to log of q, and we know that beta pressure times volume is equal to log of z, right? This is something we know. Let's try to see if we can proceed further from here. On top of that, we know that A, what is the formula for the Helmholtz energy? That is average energy minus Ts, right? So this, but for we don't have quite average number of particle yet. So how do we do that? For that, we think about the Gibbs energy, which is given by mu times the average number of particle, right? So that itself is E plus PV minus TS. So let's number these equations. 6, 7. So our connection between the two partition functions will come by looking at the connection between corresponding thermodynamic state functions, okay? So if we look at equation 7, multiply this bit of manipulations for a little bit might seem like magic or ugly, whatever you want to call it, but once you go through it again, you will see that we didn't really do anything profound. Beta mu n is equal to beta E plus beta PV minus beta TS, okay? Or beta mu n, we realize that beta E minus beta TS has been seen here in equation 6, right? So this can be written as beta times A, these two things together, plus beta PV. Beta PV is ln Z, right? So we have beta mu average n is equal to beta A plus ln Z. We are almost there now, and we have a relation because we know minus beta is equal to ln Q. So beta mu average n is equal to minus ln Q plus ln Z, or ln Q is equal to minus beta mu average n plus ln Z. This has nothing to do with quantum statistics or anything. This is just a general relation that you should try to derive on your own too, and it will make more sense, this set of manipulations. Now we can use our formula, use equation 1, which we wrote down, the first thing, the value of Z in equation 8. Use equation 1 in equation 8 to get ln Q is equal to minus beta mu average n plus what was Z? Z was product of this thing plus minus 1. So that's going to be ln product over J 1 plus minus e to the power minus beta epsilon J minus mu plus minus 1. This plus minus 1 I can bring outside to the ln. So this becomes minus beta mu n plus minus ln, right? Because it's log of something to the power, that power can come outside. Product over J 1 plus minus e to the power. And let's write it as plus beta, then it becomes mu minus epsilon J. Okay. Now it's a ln over product, so it becomes a sum over ln. So this becomes, the reason I like this formula, this derivation, which we are doing right now very much, is if I'm correct, this is the only time you will see Stirling's formula being used in reverse. Normally, Stirling's formula comes up by writing ln n factorial and saying, oh, that's too hard, that's too complicated, let's approximate it. This time, you will see it being used in reverse, and hopefully you like it as much as I do. So this will be plus minus summation over J ln of 1 plus minus e to the power plus beta mu minus epsilon J. Okay. Notice we haven't yet made any approximations about classical limit to get to equation 9, right? All that business that we did about average Nj being smaller than 1, we haven't used it yet. So let's try to use it. So average Nj much smaller than 1 over here was the same as saying e to the power beta epsilon J minus mu much more than 1, right? So we can write down here, this is the same as e to the power beta epsilon J minus mu much more than 1. And we saw this previously on page 3. Therefore, e to the power beta mu minus epsilon J is much smaller than 1, right? Now, we also know that ln of 1 plus minus x is approximately plus minus x if x is small, right? So notice here that this thing which is much smaller than 1 is exactly the thing that shows up over here, right? So if you substitute this as x, then this is ln of 1 plus minus x, right? And we can just remove the ln and change it to a plus minus x. Therefore, ln q is equal to minus beta, and approximately, now comes the approximation, minus beta mu average n plus minus sum over j, and I will write this formula again on the next page, plus minus e to the power beta mu minus epsilon j. So notice something else happened. The plus minus for Fermi-Dirac is accompanied by the plus minus are accompanied by proportionate plus minus. So let's call this equation 10, and I'm going to write down equation 10 again on next page. So we just showed ln q is equal to minus beta mu average n plus minus summation j plus minus e to the power beta mu minus epsilon j, right? So this plus minus show up symmetrically, which is wonderful, because now for either Fermi-Dirac or Bose-Einstein, this just becomes plus j e to the power beta mu minus epsilon j for Fermi-Dirac or Bose-Einstein, which is nice. So we are already starting to see some sort of nice behavior coming out. Have we seen this before in the low density limit? Just to wake everyone up. Where did we see it? We just saw it shortly ago. Can you go through your notes if you have taken them? What is that thing? It's on this page. Summation j e to the power beta mu minus epsilon j. This thing. Do you see it? Someone has to help me or I'm stuck.
It's NJ,
Yeah.
average of NJ.
Average of nj or summation j over average of nj.
Ah, yeah,
I included the summation here, Kishle, right?
yeah. Sorry.
So what is it? What is average? What is summation j over average of nj? That is average n. So ln q is equal to minus beta mu average n plus average n. That's super interesting. However, at the same time, we also showed that e to the power beta mu is equal to this thing. So let's actually, these equations we should number. This was 5. I have another 5. That's not very good. Let's call this 5c. Let's call this 5b. And let's call this 5a. So using 5a. However, 5b says that e to the power beta mu is equal to average n by summation j e to the power minus beta epsilon j. So let's use this and get rid of the beta mu in this equation. Therefore, beta mu is equal to log of whole thing, right? So beta mu is equal to log of average n minus log of summation j e to the power minus beta epsilon j. Let's call this 11. Let's call this 12. Put 12 in 11. What do we get? ln q is equal to minus beta mu. So this thing minus ln average n. Let's hope I don't make a sign error. So minus beta mu is minus ln average n plus ln j e to the power minus beta epsilon j multiplied by average n plus average n is equal to minus, and I'm just going to call average n as n, okay? Otherwise it's because we are in the thermodynamics limit. So let's say there is n, which is some number which I have observed in thermodynamics. So this is minus n ln n plus n that I had outside plus n ln summation j e to the power minus beta epsilon j. This is what I meant by using Stirling's formula in opposite. I can't think of any other time where I've seen this happen, but it happens in this derivation. This is minus ln n factorial, right? So we have just shown that ln q is equal to minus ln n factorial plus n ln summation j e to the power minus beta epsilon j, or ln q is equal to ln of summation j e to the power minus beta epsilon j whole to the power n, because this n can go here and become power, divided by n factorial. And now, or now we have ln on both sides, we can just remove it. Q is equal to 1 over n factorial summation j e to the power minus beta epsilon j whole to the power n. This is
Quick information about the derivation on the last page.
Mhm.
So here you explicitly write down n is equal to the average of n. So does that mean that the whole derivation, say, can only be applied to the massive particles?
No. Actually, we are working with a canonical partition function, right?
Yeah, but here, like, you explicitly write down the mu's and stuff, which means
There is a reason. So let's look from here. Do you see any mu starting here? There is no mu, right?
Yes.
And in a canonical partition function, n is fixed.
Yes, correct.
That's why we did this. So
Yeah, but I was referring to like the one, the expression of the average value of n.
correct. But in this one, I did not set average n is equal to n. I did not do that. I did this approximation that average n is equal to n only when I had gotten rid of my mu. So it's consistent.
Okay, I see.
See, it's clever and consistent. The approximation happened only at the right time. And also, if it really bothers you, you keep average n over here. There is nothing wrong about it. I just didn't want to write bracket all the time. If you want, you can write it as average n. It's exact. But we are talking about canonical partition function now, in which n is there. And also in thermodynamic limit, we are talking about low density. We are talking about thermodynamics. So it's okay to do that. But it's not just okay. It's actually correct because we are talking about a canonical partition function. It's a good question. So
Okay.
we just recovered our ansatz, what we thought should prevail. Equation 3. This is exactly equation 3. Or equation 3. So our Fermi-Dirac and Bose-Einstein setup, first of all, it led to average number of particles in a state being proportional to the Boltzmann factor, which is something we expect in classical distribution. Note, this is not true in quantum statistics. In quantum statistics, average value of nj is not simply Boltzmann factor. So that's really the key home, take home message. One of the take home messages here is that nj classical, most of the times, most of you will not be worrying about quantum mechanics, right? If you want to think about anything in life, most likely you will be using some sort of classical approximation. But however, many of you do think about quantum mechanics heavily, so it's not always true. So, but for a classical particle, average nj is equal to average n e to the power minus beta epsilon j by summation j e to the power minus beta epsilon j. Average nj for a Fermi-Dirac type of particle is equal to 1 over e to the power beta epsilon j minus mu, and you can always remember this will be plus 1 because it won't otherwise this one cannot diverge, and average nj Bose-Einstein is equal to 1 over e to the power beta epsilon j minus mu minus 1. And notice in the second and third, let's call this collectively as equation 13. In the second and third equation, I don't have average n, I have chemical mu. In the first equation, I have average n, and that's where those manipulations that we did come into help, equation number 12. And in the classical, high temperature, low density limit, NJFD and NJ Bose-Einstein reduce to or converge to nj classical, which we just showed. And in that case, the partition function could have been written through this simple argument that just write down the partition function for one particle by summing over all states, take it to the power n, and then divide by n factorial. So one thing I want you to think about as an exercise, and I promise you it will show up either in an exam or in a midterm. It will show up at some point. So homework or do it yourself is, what would happen if, like Nathan did this earlier this class, if I ignored the n factorial in equation 3. If I wrote q is equal to summation j e to the power minus beta epsilon j to the power n, and try to get, and your hint here is to, what should I give you? This is, let's think about ideal gas of structureless particles, okay? So you can write down the canonical, you can write down the single particle partition function. You can write down q is equal to q1 to the power n, and you can calculate q1 for an ideal gas. We have done this, right? We have calculated the particle function for an ideal gas. How do we do this? We go to phase space, we write dr dp, we write e to the power minus beta potential energy plus kinetic energy. We separate those integrals. It's an ideal gas, so potential energy does not matter. Kinetic energy is p squared over 2m. So you do all this, but ignore this first term, okay? Ignore this 1 over n factorial. You will come to some paradoxes, and I want you to think about what are those paradoxes, and then I want you to add n factorial and see how those paradoxes are resolved, okay? So think through this. I will ask you this in an exam or a midterm. So if you work through this on your own, it will make you feel quite pleased with yourself, I can promise you. I felt that way. It was like, wow, I finally understand something. So try that out. Any questions? Okay, so let's think a bit more about the validity of this classical approximation. Qn, n particle partition function is equal to q1 to the power n by n factorial. So when is this approximation valid? So what did we do here? So what we are saying is that we saw that indistinguishability, and in order to see that this indistinguishability matters, that you have to derive by n factorial, you will have to go and solve for my paradox and see what happens. But you also saw that the n factorial, even if you, so we could have just written equation 3 by saying, oh, it's indistinguishable, so divide by n factorial. But we didn't do that. We worked through the full thing and we came out to this conclusion. We used Stirling's formula in an opposite way, and then we got the ln n factorial, right? So it came out. But so basically we saw that the indistinguishability of molecules cannot be discarded even when particles are treated classically, right? So even if you treat them classically, you have to account for this n factorial. It's a strange conclusion. It's a non-intuitive conclusion. So I want everyone to think about it, because the more you think about it, the more confused you will get, and that's a good thing. And then it will become clearer, because it's subtle. Why did we have this n factorial? we went through the full derivation and we saw it came out. And I will give you the name here. It's called Gibbs paradox. When Gibbs was first trying to do it, he wouldn't divide by n factorial and he would lead to all kinds of funky things. So, and the only way he could come up with and to say that, oh, no, classical particles are indistinguishable, which is strange. But anyway, we do, however, assume classical mechanics in doing this. So what we want to see here is when is this classical approximation that Q1, every particle can be treated classically is valid. So this is something similar to what we see in quantum mechanics. The classical approximation is valid when the uncertainty in position x multiplied by uncertainty in momentum p is much more than h cut, right? We know this is uncertainty principle. So if we can show that this is the regime that we are in, then we are okay to use classical mechanics in order to write this down as dr dp e to the power minus beta p plus ke and not worry about Schrodinger equation and things like that. So how do we do that? So if mean momentum of particles is p bar and mean separation is r bar, and if p bar multiplied by r bar is much more than Planck's constant, then we are okay. That's the idea. Okay, that if the mean, so you might be a bit uncomfortable here because here we are talking about errors and here we are talking about mean, but this is really a hand waving argument that I'm doing here, that the mean value of momentum multiplied by the mean value of position, interparticle separation, if it's much more than h bar, then we are okay. And the argument behind replacing, so we are conflating mean with standard deviation, and that is okay for Gaussians, right? If things were behaving as Gaussians, then there is some, do I really want to go down this line? No, I don't want to go down this line. I'm just making a hard, I was trying to justify it further, but I won't try. So the idea being that but this is something we have done in PCAM when we do uncertainty principle, right? We try to see why don't we use uncertainty principle for a tennis ball or a baseball or something like that. And this is type the argument we use. Or if R bar, if the mean separation between particles is much more than h cut divided by p bar, we are okay. H cut divided by p bar has a name in quantum mechanics. This is called the de Broglie wavelength. Right? So if the mean separation between particles is more than de Broglie wavelength, then we are okay. And again, if this bothers you, go and read up Wikipedia. I mean, this is something we do a lot in quantum mechanics. So, but now let's calculate R bar. What is R bar? R bar is going to be roughly the volume of the particle divided by number to the power 1/3. Right? If we assume kind of spherical description, then R bar is approximately this. Where did this come from? R cube is proportional to V over N or proportional to density, right? Density is proportional to the, and this is not, so this is the average separation between particles, right? So that's the idea over here. So R bar is approximately V divided by N to the power 1/3. What can we say about P bar? We can use equipartition. We can say that 1/2m P bar square must be equal to 3/2 kT, right? So let's call this equation 14, this as equation 15, this as equation 16. So we use our condition of the de Broglie wavelength and put down these values. So we are saying that if V by n to the power 1 by 3 is much more than h bar divided by square root of 3 mkt, we are okay. And or the density much more than h cut by square root of 3 mkt to the power 3. So again, a DIY, put in value of h bar, put in T equal to 300 Kelvin, put in the value of Boltzmann constant, and see what density you get over here. You will see it's a very, 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 very small number at room temperature. If you start to make the temperature smaller, of course, this cutoff value for the density starts to go up, right? So at room temperature, this is a very small number. So any density, for example, the density of water is 1 gram per centimeter cube, will be much higher than the value you get through to de Broglie wavelength. So the classical approximation is okay. But as the temperature goes down, rho cutoff shoots up, and most materials will not be, or most molecules will not be following this property. So if you decrease the temperature, quantum mechanics starts to prevail, which is something we all know, and that's the full picture over here. Okay, any questions about this?
I do not understand why this density comes from. If it is the number density, then it should be n over v, right? It seems like an inverse density or whatever.
Mm-hmm. You're absolutely correct. And that was leading to a contradiction. Good. So we just wrote V by n to the power 1 by 3 is much more than h cut over square root of 3 mkt, or rho to the power minus 1 over 3, correct? Rho is equal to n over v, much more than h cut square root 3 mkt. So what you pointed out that we were contradicting ourselves. We were saying classical mechanics will function at high density. That's not true, right? Or rho to the power 1 by 3 is much smaller than square root 3 mkt by h cut, okay? Or rho is much smaller than square root 3 mkt by h cut to the power cube. Now, h cut is typically 10 to the power minus 34, right? So you have 10 to the power minus 34 here in the denominator. And if temperature is also high enough and you take the cube of this thing, this is going to be 10 to the power 100 or something, right? In some units. Therefore, this rho cut, classical mechanics at rho less than a cutoff density, rho cut is absurdly high at room temperature. However, as temperature, this is pretty terrible, however, as temperature goes down to 0, you can see the rho cut value will start to become smaller and smaller. Okay, who was it? Did Z point this out, this error? I don't know who it was, I have forgotten.
Yeah,
Okay, are you happy now, Z?
yeah.
Good, thank you for pointing it out. I was myself scratching my beard as to, wait, why am I saying that at high density classical mechanics will start to dominate? That's the opposite of what we wrote in this box picture, right? Putting particles in a certain box. We were talking about low density. And this, how low should it be? We just quantified it we are quite tolerant because square root of 3 mkt by h cut to the power cube is such a large number because of h cut being such a small number that, and again, you might recall here that depending on m, electrons have a very small m, right? So for electrons, this thing is actually, you might get quantum effects earlier as compared to things that are much heavier than electrons, right? So you can see that type of electrons have low m, so the cutoff, therefore rho cut is small relatively. But at a high enough temperature, at room temperature, most things are classical. So this is a good metric. This expression might be one of those things that you find quite useful in future. Whenever you think you should do classical mechanics or quantum mechanics, take the mass of whatever you're looking at, put in the temperature and see what value you get, see the density of that material and see, okay, well, it's kind of much smaller than the value I got over here. So I think classical mechanics is okay. So I'm going to stop here, but I will introduce the topic that we are going to study next time, next class, which is the free electron model for metals. And again, this will be valid at low temperature and high density. So the opposite of what we wrote. We are going to be in the regime where quantum mechanics dominates. And we are going to solve two mysteries next time that classical mechanics could not solve. The first mystery, so, was that the heat capacity per electron would be much smaller than 3/2 Nk, even at high temperature. And secondly, the heat capacity at low temperature would be proportional to T. So why is the first one perplexing? The first one is perplexing because what difference would this first observation lead to between insulator and metal? Given that one is true, what difference do you expect to see between the heat capacity of an insulator and that of a metal as you increase the temperature? Any idea? Should they be the same or should they be the different? Should they be different? So the difference between an insulator and a metal is the presence of electrons. So people were perplexed that they heated an insulator to a high temperature and they heated a metal to a high temperature, even though they had different electrons. And in a metal, the reason why they should shock you, in a metal, there are electrons which are at the Fermi surface, they're moving around everywhere. And you think, wow, their heat capacity should be so different because I don't have to just excite the atoms, I can excite the electrons close to the Fermi surface. It's gonna be wonderful. But turns out there is no difference. Insulators and metals at high temperature have the similar heat capacity. The difference is less than 10% between insulator and metal. Very, very small difference. And secondly, when you go to low temperature, there is a difference. If you have an insulator at low temperature, its heat capacity behaves as AT cube. But for a metal at very low temperature, the heat capacity behaves as BT. And this was also not explainable. So a better model for heat capacity is AT cube plus BT, where AT cube arises from the lattice contribution and BT arises from the electronic contribution. And as you decrease the temperature, the T cube term dies off quicker. And in the end, you are left with only BT. So just to summarize, for next time, we are going to show as to electron versus, insulator versus metal, same heat capacity at high T, different heat capacity as T tends to 0. In fact, the difference is proportional to temperature. And this is what we are going to study in the next class. Okay, So any more questions? Otherwise, we are done for the day. So go through all of this. Nothing here was profound, but it was a bunch of manipulations. So please go through it, take your time, that everything makes sense. If you have any questions, please post on Slack. If you ask me lots of questions on Slack, you will get 20 participation points. You can rest assured about that. So please keep asking me questions. Okay? Otherwise, see you on Thursday.